Hi, I'm JJ, and today I'm going to be showing you a couple of activities that can be done as demonstrations in your classroom that have to do with centripetal force and centripetal acceleration. We're going to be doing those using Pasco's new wireless force acceleration sensor and this rotating stage. Now, I'm using this rotating stage, but both of these activities can be done on things like a rotating stool or a rotating table or even like a record player. Just got to make sure that if you use those that you secure the sensor so it doesn't slide around when the table is rotating. Okay, so for the first activity, what we're going to do is we're going to try to establish a relationship between centripetal acceleration and angular velocity. Now, to establish that, we're going to be using measurements from the built-in sensors inside this wireless force acceleration sensor. One of those sensors is a 3-axis accelerometer, and the other is a 3-axis gyroscope. And there's also a built-in force sensor here that we'll be using for the second activity. Now, to establish the relationship between centripetal acceleration and angular velocity, we have to make sure that our frame of reference and the directionality of our measurements is all consistent. And what I mean is, the sensor measures acceleration in 3 directions, and we want to make sure that it's measuring centripetal acceleration, which points to the center or the axis of rotation of our stage. And we can tell which axis that is by looking at the small diagram on the top of the sensor here. It indicates Y is in this direction, Z is up out of the sensor, and X is in this direction. So we're going to be measuring centripetal acceleration in the X direction. And now also, the same diagram is used for the directionality associated with the gyroscope. And because the stage rotates this way, we were going to be measuring rotation about the Z-axis, which comes up out of the center of the stage. And using the right-hand rule, we know that if we look down on the stage and it's rotating counterclockwise, that's the positive Z direction. Okay, so I have a capstone file set up here that shows acceleration in the X direction versus angular velocity in the Z direction. So to establish this relationship, we'll just go ahead and spin the stage here and record some data and see what it looks like. Zoom in, and I'm going to pinch the axle here just to slow it down to help speed things up a little bit. And in fact, when it gets to 0, I'm going to use my hands to spin it the other direction and slow it down again. All right. And we see what looks like a parabolic relationship here between centripetal acceleration and angular velocity. And to see if it is in fact a squared relationship where centripetal acceleration is proportional to the square of angular velocity, we can use these functions in Capstone called quick calcs, where I can quickly change either the X or Y axis and manipulate it mathematically to show me the square of that value. And if you look at this graph, angular acceleration versus angular velocity squared, it looks like a nice straight line, which denotes that the centripetal acceleration is proportional to the square of the angular velocity. Now, we've discovered or established that relationship between centripetal acceleration and angular velocity, but what happens if we change another variable? Let's say the distance from the sensor to the center or the axis of rotation on the stage here. So what I'm going to do is I'm just going to move this guy out, double the distance here, and spin the stage up and collect some more data. Again, I'm going to just pinch the axle here to speed this up. Great. And we can see here that obviously there was an effect. So increasing the radius increased the slope of that curve on our acceleration versus angular velocity squared graph. And now, what exactly is that relationship? Well, let's put on a couple of linear curve fits here and take a look at the slopes. Okay, and you can see here that there's about a factor of 2 difference between the slopes. And there was also a factor of 2 difference in terms of the distance between the axis of rotation and the position of the sensor as it was rotating, or the radius of the sensor. So doubling the distance between the axis of rotation and the sensor also doubled the slope. So we can see that this also denotes that there's a proportional relationship between centripetal acceleration and the distance between the sensor and the axis of rotation. So we were looking at the relationship between centripetal acceleration, and a couple of variables. Now let's take a look at some relationships that exist between centripetal force and, let's say, the amount of mass in an object that's rotating about an axis. And to do that, I'm going to use a small mass tied to a piece of string here. And all I'm going to do is set this on the stage and then attach it to the hook on the sensor here. So now, when I spin the stage, there's going to be some forces that are experienced by the mass and the tension in the string here. We're going to use the sensor to measure those while simultaneously measuring the angular velocity. So for this activity, I'm going to be looking at a graph of force, or in this case, it's centripetal force, versus angular velocity squared, again, in the z direction. So I'm going to go ahead and spin the stage and start recording data. And we see here that the data is relatively linear, right? So now, what do we think the effect is going to be if we double the mass attached to the end of the force sensor here? And to test that, I've got another set of masses here, twice as much attached to a string that has equal length, meaning we're going to keep the radius or the distance between the mass and the axis of rotation constant, because we're testing this variable and not any of the other variables. I'm going to go ahead and spin the stage. Begin recording data. I'm going to go ahead and stop after recording a little bit of data here. And we can see in both of these runs that it's a relatively linear relationship. And in fact, if we applied curve fits like we did previously, linear curve fits, we can see that there is about a factor of 2 difference between the slopes. And there was also a factor of 2 difference between the amount of mass that was attached to the end of the sensor. Twice as much mass, doubled the slopes of these lines, which also denotes that there's a proportional relationship between centripetal force and the amount of mass attached. So these are just 2 of many activities that we can do that take advantage of the built-in sensors inside the Pasco wireless force acceleration sensor. So thanks for joining us.